So, hello, Seattle. I made it here about a week ago and started hanging out with Bartosz. I showed up with short hair. Now I have gone full-on category theorist. I'm going to do the thing here in a editor window. So what I want to talk about today are a number of abstractions that lie between the ones that we usually use, maybe. How many people here are comfortable with monoids? All right, good. We're at a functional programming conference. How many people are not comfortable with monoids? Let's start there. Okay, so I apologize. I will give the laws, and I'll give a couple of examples, but I'm going to go pretty far past them pretty quickly. How many people here are comfortable with groups? Okay, so some people have taken some more math classes. So let's see. What I'm looking for are, I'll just build like a basic little numeric hierarchy of these things. Is this a resolution people can see? So I'll start with, monoid and then I'll dumb it down. So in Haskell we would have something like this, m to m to m, and mempty, such that mempty appended with a is a appended with mempty. And I say appended because the real name that they give this thing is this awful mess. Historical reasons. And we often factor out a common, like a superclass of this, or we are doing so now. This just went into Haskell, which moves this up to here. So I apologize to those of you who don't read Haskell. Think of this as like almost like an interface or something like that of what it is you want to allow for operations. That will get you by. So we have these things, and we have in semigroup just that A appended with B appended with C is A appended with B appended with C, where the parens are shuffled around. So what is this? This would be something like addition with 0. We can put the parentheses wherever we want in a sequence of additions. We can put zeros in and add them in. It doesn't really matter. These have become kind of important in distributed data processing and stuff like that, just because if I have a monoid that I want to compute over a big data set, I can turn around and put the parens around the data that's on one machine and on the other machines, and then kind of add it all up and get the answer. So if you take nothing else away from it, from this, monoids are cool. Go look at them. You'll find them all over the place in your code. Okay, now the notion of a group. We don't actually have packaged up in Haskell. Adds a notion of inverse here, such that if I have any element x, x appended with the inverse of x is the unit. But there's other things between semigroup and group that I want to talk about today. So I just wanted to kind of poke at where it is in the mathematical hierarchy I'm interested in rambling on about. Mostly because when Bartosz invited me out here to come out and give a talk, I said, well, I might as well come out and give a talk about a pile of abstractions he hasn't had a chance to use. Maybe we'll get some new blog posts out of it or something. And then I turned around and looked the other day, and there's all sorts of uses for inverse semigroups and these things that I'm going to talk about in physics, so maybe. All right. So what is it that I want to poke at? There's a bunch of things that lie between semigroup and group that act, where they have something that almost acts like an inverse. I should be careful not to get too far away from the mic. I apologize for recording purposes. What I want is something like, let me actually give it a, okay, showcasing examples for inverses for addition is negation, inverses for multiplication is reciprocal. There are things that are monoids that are not groups. Just to give an example, like max, and integers with maximum would give me, well, integers will give me just a semigroup because there's no unit. I don't have a least integer. Naturals, I do have a least natural. Int, where I have just like limited myself to numbers that I can fit into a 32-bit register or something like that. There I can go down to min bound or whatever's the smallest representable number that I can fit. So you wind up hitting these different points in the hierarchy that we have so far for different data types. Okay, so just to show that they're distinctly inhabitable and meaningfully separable. Another point that I'm going to be talking about a fair bit here will be the notion of a semilattice. I'm going to be talking about joined semilattices. Usually if you see any of the literature on the stuff I'm going to talk about, they'll use meet semilattices. But all I'm going to be saying when I say that I have a semilattice is that A appended with B is B appended with A, and A appended with A is A. So this is idempotent, and it is commutative. So max would pass this test, but does not have an inverse. So in some sense, the thing that I want to talk about today is sort of the least generalization of a group and a semilattice. And so I'm going to make I'll just go to sketch of it. I'm going to talk about a regular or an inverse semigroup, which is going to be a semigroup M, where we still have this notion of an inverse, but inverse doesn't mean everything we expected it to mean. And then we'd be able to refactor this hierarchy to say that semilattices and groups are inverse semigroups. So the operation that I want here is going to give me a law something like x appended with inverse of x appended with x is x. And the inverse of x appended with inverse of x is inverse of x. How's that for a pile of symbols? Okay. So this is the toy that I'm going to be playing with. There's a couple of extra conditions here. What I've written is technically something I'll call a regular semigroup, and then inverse semigroups add a couple more things on top. And I'll try and give some examples that actually showcase what the heck I'm talking about and maybe a little bit about why it's interesting. Okay. So I'm going to skip ahead to actually building one of these. And the example I'm going to use is just fiddling around with piles of parentheses. Okay, so let's say you had any sort of soup of parentheses that you wanted to check to see if it was balanced. Might not show up so well as distinct symbols. But we can go through and just kill off all the paired ones. If you had, if this original string was a balanced set of parentheses, then the string that I would get after I looked for any pairs of parentheses that were facing into each other and removed them would also be balanced. If this new string is balanced, then the old string was balanced. So now what I can do is I can summarize this by just saying there's two numbers. The number of outward-facing parens that I couldn't cancel facing left, and the number of outward-facing parens I couldn't cancel facing right, for instance. So I could just make a data type that holds on to those two numbers. And then so now we can see them. And then I could make a semigroup for this. How's this going to work? BAB appended with BCD is going to be something like that. I have A many parens facing this way, B many parens facing this way, C many parens facing this way, D many parens facing that way. And now I want to cancel out the B's with the C's and let the excess overflow one way or the other. So if I have fewer b's than c's, like I do in this example right here, then what I get is b of, like, I've got the a's plus the c's minus the b's. So I've got the excess c's. Otherwise, we go and we have an a and then a d plus a b minus a c. And this happens to be a monoid. And then the monoid here is B00. And so I might be able to do something like parse, taking a single character and giving me an element of this thing, just to say if I wanted to check to see if all the parentheses in a string were balanced. I would use parse of opening paren is 1 opening paren. Parse of a closing paren is 1 closing paren. Parse of everything else is nothing. And then we have fold map in Haskell, which says if you give me a function from a to some monoid m, I will take a list of a to a monoid m, or any foldable container full of a's. So we have this guy. So I can use this to say checking if something is balanced is just fold map with parse over my string, and then checking to see if that is the empty set of parentheses. Let me comment out the rest of this stuff up here and actually see if I can type check this code. And with luck, in front of a live studio audience, I didn't make a typo. That just is balanced. This is not. And this properly handles outward facing parens, etc. So the thing that we just invented is something called the bicyclic semigroup. In math, it's the semigroup generated by two objects such that they cancel in one direction. You have A, B as E, but nothing else. It's the free semigroup with such a condition. They call it the bicyclic semigroup, even though it's a monoid, because, I don't know, they came up with it before they really started caring about monoids. But it is also an example of something where there's almost an inverse. There's not really an inverse, right? There's nothing I could do. If I had some number of parens facing this way, and maybe some facing this way, nothing I can do on this right-hand side can get rid of these 3 parens. Like, they're stuck. I can't close them on this side. So I can't actually be a proper inverse. But what I can come up with is something that I could say, you know, given this A and B, how would I come up with something I could do over here such that if I did this again, I get back to that. And the easiest solution, or the only solution that works, is to just kind of flip the parentheses around. Because if I were to repeat myself the opposite direction, these B's will cancel out perfectly, these A's will cancel out perfectly. And I'll be left with A, B. So the outermost parens and these outermost parens are the ones we're left with, and these inner sets cancel out. A lot of my examples today are going to come from parsing, because this is where I started tripping over these problems, so be warned. If you don't care about parsing, maybe you won't care about these problems, but they will come up in unification and a bunch of other places as we go. I don't know how much that I'll have time to fit into this slot, but feel free to ambush me later, and we can talk about other things. Okay, so we have systems of balanced parentheses give me a notion of sort of an inverse. that satisfies this condition, that if I were to take something and then turn it around, I can at least undo the damage that this thing did so that I could do it again. So this is one of the conditions to be an inverse semigroup. But there's another couple of conditions that are less obviously stated. So all idempotents are of the form x appended inverse x, or y equals for some x. And all idempotents commute. These are the two extra funny conditions you get if you ever look up the definition of an inverse semigroup on Wikipedia. And so what the heck is that saying? So all idempotents being of this form, well, what would happen if we were to take an element and smash it with its own inverse here? Inverse in this scare quote sense. So we have some number of parens facing left, then right, then we have this thing here, right? So these b's, whatever they are going to cancel with each other, leaving me with some natural number with a parentheses facing outward in both directions. Okay? And then if I were to smash this together with another one, well, what's going to happen? We're going to kind of eat off whichever one has fewer elements is going to eat off some number of parens from one and then put it right back. So this will actually compute the max of those two natural numbers. So earlier we were saying that max was commutative. So just playing with parentheses, we start seeing max and natural numbers showing up. It's a little odd to me. So what are the idempotent elements here? The idempotent elements of my system of balanced parentheses are the cases when I have the same number of parens facing out in both directions. Those are the ones that we get when we're talking about x composed with inverse x. And max is commutative, therefore all idempotent elements commute with each other. I don't know, I was kind of surprised to stumble over that structure here when I was playing around with this. And some of this is me playing around with math and trying to see, there's a whole bunch of literature on this stuff. Can I transport any of it into Haskell and use it as a tool in my day-to-day existence? So I was introduced to this this area of math from a person who works over at Obsidian Systems, Dan Haraj. So just for provenance of ideas, Dan is the one who infected me with this obsession with inverse semigroups. Okay, so there are things that satisfy these first two laws that do not satisfy these laws, like we picked up with the parentheses. And so I think a significant portion of the rest of my time will be poking at what those things are and just kind of trying to see if we can identify some of them in practice. And one of them that is kind of near and dear to my heart, and I think this is a little bit more Scala-heavy crowd than Haskell-heavy, if I'm guessing right? All right. Let's see if I can go back to my slides here. So if we look at the definition of, on Wikipedia, of examples of regular semigroups, these do not seem like things that we are going to go find in the real world in any way, shape, or form. They're like, every group is a regular semigroup. Every band and the bicyclic semigroup we just talked about, the full transformation semigroup, all these other funny things. But I'm going to try and find something a little closer to home. Well, maybe not exactly close to home. I go down to Australia fairly regularly, and there was a joke account active for a while, Haskell CEO, a couple years ago. And it seems like whenever I go around and run into functional programmers, there's always an Australian in the room. And I think the reason comes from another Haskell CEO quote. Between 1788 and 1868, approximately 165,000 convicts were transported to various parts of Australia. All of them were category theorists. And I believe the teaser or the bio section for me had me listed as working for Standard & Poor's, which was a couple of jobs ago. I currently work for an organization called MIRI, the Machine Intelligence Research Institute, which does a lot of research on AI in general and AI risk factors and a whole bunch of things there. If anybody wants to talk to me about that, feel free to come up to me afterwards. But in some sense, I do believe that a significant portion of Australia has already been replaced by AI. And the proof that I offer comes in the form of a cartoon, which can be parsed by Australians. And so I will introduce you to Australian binary here. Hold on, let me see if I've got my audio working. Oh no. Here we go. Go into the Elgato capture card. I am getting So that is actually parsable by folks, at least in like parts of New Zealand and like from like Sydney up through Brisbane, maybe a little parts north. I see a couple of folks who might be from Australia nodding along. And so I will give my non-Australian parse of this and maybe see if we can interpret this. So I've seen multiple sort of etymologies of what this is, or definitions of what this is supposed to mean, the yeah, nah, and nah, yeah. The one that is parsed to my American brain is to sort of hear yeah, nah as I hear you, but nah. And nah, yeah is I didn't believe you, but okay. All right. So if we were to take that, right, we're going to get a truth table that looks something like yeah, nah is nah. And nah, yeah is yeah. And yeah, yeah is yeah. And nah, nah is nah. So this is my Australian binary truth table. And so you can view this as like compressing that entire long string down to the last thing that someone said. This is one possible truth table that one could assign to this. I will argue that if you look at Reddit, and rstraya has a truth table, as it were, that kind of summarizes the same Cayley table of how things work out, and they give a different answer. So there's either regional variation or I'm just wrong. This is also not sufficiently sarcastic, and there's all sorts of other problems, but to really be an Australian truth table. Another way to think about it maybe is like, think of it like an exponential moving average, right? You're like just exponential decay. The older ones are like, like contributing less weight. And then if you were to decay at 50%, you could actually approximate any confidence level in the statement, right? You can actually work out like the bit string for any percentage. So that might be a better one. That was what I came up with the other day when I was actually trying to put down this in code. But whatever you have, this like turns out to be bigger than binary. At least once we start making this. So this version we can recognize. In Haskell, in the semigroups library, I put a monoid named last. This just gives you, there's a semigroup named last. It just gives you the last thing you saw. This is a semigroup, not a monoid, but it's okay. We're talking about inverse semigroups and things today. And so in order for this to be an inverse semigroup, I would need some kind of inverse that I could shove in the middle. That should be uniquely determined. That's the other clause I want to say. And I have idempotence, and all idempotents commute and stuff like that. Nothing commutes here. That's the first sign that something's going to go wrong. If I swap the order of yeah and nah, I totally get a different answer. So we're not going to be an inverse semigroup. So we're going to need to invent something that comes a little bit above it, which we'll call a regular semigroup. And for right now, I'll say that inverse just moves up here with these two laws, and we're left with regular semigroups. Okay, so Australian English, or at least this truth table, passes the test to be an inverse semigroup. I have an inverse. If I had like yeah, something, something, yeah, I can get yeah just by putting like nah in there. And nah, yeah, nah is nah. So far so good, except for the fact that yeah, yeah, yeah is also good. So we now have two things that pass the test. Nah, nah, nah is nah. Right, so far our inverses are not unique. We've failed to isolate what the real inverse is. So when mathematicians will talk about regular semigroups, they'll talk about pseudo-inverses. So elements that you can kind of sandwich in the middle. And in the regular semigroup case, they're not necessarily unique. That's what we're seeing here. So Australian English, this yeah, nah, yeah thing that we've invented so far, passes the test to be a regular semigroup, but will not pass the test to be an inverse semigroup. The inverses are not unique. There's no idempotent elements. I mostly just wanted an example that was not one of the ones like that out of that Wikipedia page, and this is the one that came to mind. I was down visiting the Queensland Functional Programming Lab, where Tony Morris and a bunch of other folks are, and so this came up in conversation. One thing worth noting is this is, again, not sufficiently sarcastic to be properly Australian. I think those of you who know Tony will know that if he's constantly agreeing with you, he's really taking the piss. And so this is nah. And this probably is, this like self-denial thing is really yeah. But if I were to go through and like put this truth table together, I don't even get anything associative. So on the other hand, I do get unique inverses. So I don't know. That means like what I would have to do is like lock the associativity to one direction, like always associate to the right-hand side. And if I did this with slides, I would sit there and say, well, now we'll take the difference list of these, and then we'll try and find like a set of things that is isomorphic to the difference list, and then spit out a larger thing to show how Australians have managed to cram more than two values into true and false. But this is the general shape of Australian English that I wanted to talk about today. So why do I care about these things in general? So I think that's everything I'm going to talk about for Australian English. Maybe for a follow-up talk, I can do MATE, or their rating system of not bad, which goes from not bad to not bad. But so where do these come up in practice? So one of the other examples that where this started showing itself when I was just working on general problems with programming stuff, a guy, Alan Zimmerman, who does the Haskell language server protocol implementation, Haskell Osp, which is built on the Haskell IDE engine that he also works on, I believe. He was trying to reduce improve the responsiveness of the Haskell IDE engine. So the language server protocol, how many people here do not know what I mean by language server protocol? Okay, how many people do? All right, that between the two, somewhere in the middle is the actual answer. The law of excluded middle. It's not active here. So language server protocol is a thing that Microsoft pushed out with like Visual Studio Code to try and make it so that if I write a language, I can turn around and tell you how I deal with renaming and how I deal with like supplying you syntax errors and all sorts of things, like as an interactive process in when working with the compiler. And so the Haskell Osp implementation is a implementation of the language server protocol for Haskell, so that Haskell can work with Visual Studio Code, or also with Emacs and Vim and all these other editors that now have LSP plugins for sort of separating out sort of language-centric concerns with editor-centric concerns. And so the problem that is at hand is this. I just type checked a couple seconds ago. It's going to take me maybe 20 seconds to compile because Haskell's slow. You can run from your problems unless your problem is a Haskell. I'm stuck with this compiler. It's the language I'm working in. I'm fixing that. Come talk to me afterwards. But the key thing here is if the compiler is going to take 10 seconds, 20 seconds, whatever to compile a bunch of stuff, you're going to have these long pauses in which you're not going to get feedback in your editor. So there's a mapping from like old source locations to new source locations as you've been typing that you can kind of keep in check as you go. So you've got like the set of old locations and new locations. You have a mapping that's sort of a monotonic mapping of a subset of old locations to new locations, because I could have deleted some of the text that was present before. I could inserted new text. But there's a subset of old locations that correspond to new locations and vice versa. And this forms an inverse semigroup. So that if I had like a series of edits I've applied here, I can apply more edits and I can compose those together and get a bigger and better edit. So the version that Alan was originally using involved taking like int to maybe int and another int to maybe int coming back, and then just composing these Kleisli arrows, which are then being built up off of like single character edits or something like that. The problem then is that as you do lots of these small edits, these Kleisli arrows get slower and slower. It doesn't compose well. So when he asked me, well, like, how would I have tackled the problem, I said, well, there's an inverse semigroup there. Why? Because I just talked to Dan and was thinking about these inverse semigroups all the time. And so I sat down and built a little raw implementation for him, and I don't know if he's actually incorporated it yet or not. So this was a couple of months ago, or maybe going on 5 or 6 months ago. I probably should have followed up. Regardless, sorry. The idea there that we could like compose these like partial bijections between the old positions and the new positions seem to have a lot of power. It gives me a nice normal form for them. They can be encoded nicely compactly. For the category theorist in the room, you can view these as simpliciomorphisms. There's lots of nice algebraic structure there that people have already figured out how to encode optimally in order to do the category theory bits. So that turned out to be an actual pragmatic example in like things that I actually have that I care about. There's another place where this kind of comes up, which I have yet to actually find a use for. I've spotted the pattern existing. There's a proof in all the math that says the semi-direct product of a group and an inverse semigroup, or of a group and a joined semilattice yields an inverse semigroup. And so I will have enough time to kind of give a motive, like to demonstrate that, I think, but I don't have a good motivation for using it yet. So this is sort of the question. Now that I have this abstraction should let me write something that I can't write today, right? Like that's the whole point of having the abstraction, right? So this is more the call to action. Find me uses for these things and tell me, okay? I have now nested it in your brains that this thing exists. And And now I'm sending you out to try and figure out applications that actually work, or that use the abstraction. So the worked example, the semi-direct product thing, like to unpack that statement. So how many people here are comfortable with monoid actions? All right, like 5. Okay, so a monoid action is going to be something like this. I have some monoid and some other set such that there's some function act that takes M and turns it into a function from S to S in a way that makes it so. Let me get more screen space here, please. I should have done that more efficiently, but whatever. So I said if I act with mempty, I get the identity function, and if I act with M appended with N, I get the result of composing these two things. So like integers or natural numbers dropping from a list drop composes this way if I was using natural numbers. Because I can take a string to a string that is just the string with the prefix dropped. Drop of M plus N is drop, and followed by a second drop. Drop 0 things off the list, doesn't change it, etc. Okay, so this is the notion of a monoid action. And then I will go even further. So I want a monoid acting on a monoid. So now S is not just any S, but it's a thing that is a monoid in its own right. And all I'm going to add is a couple of laws here that say that if I were to act with some M on mempty, this should be mempty. If I were to act with some M on M opposed, or A composed B, or pick a name that's indicative of what I'm going to do with it later, act. So let's try and consider what these things could be. The monoid that I might be acting on could be something like sets of locations, and the monoid that I'm acting with is like a change in position. Okay, so if I were to have a set of locations and an empty set of locations and relocate it, I still get an empty set of locations. And if I were to relocate the joins, like if I were to relocate the set after I smash two sets together, I would get the same answer if I relocated the sets individually and then smashed them together. So it's pretty esoteric sounding when we just write down the laws, but if you think about it, the relocation should compose, and like relocation should distribute across using the monoid is enough to actually be able to use this thing in practice. So what I could do here is now talk about something kind of like the product. So normally we're used to saying, like, if I have a product of A and B, I have an A and a B, and I have like something like instance monoid A, monoid B, gives me monoid product AB. This is normally in Haskell just that, right? And empty here is empty. And then A, B appended with CD is A appended with C, B appended with D, right? This would be how you would take the product of two monoids. If you had two monoids that you wanted to fold over your data, you could then group them up and do them in one pass. I gave a talk on this at Boston Haskell back in like 2007, 2008 or so, and then Runar and Paul Chiasano went off and built a whole financial product at S&P about it for doing portfolio attribution and factor back testing. And so that's why I wound up at S&P way back in the day. So not terribly earth-shaking by today's standards, but it's a thing you can do. So now the concern here is these two sides are independent. So let's say that I had something like, I have an interval worth of source text, like some delta worth of position worth of input, and some set of positions inside of those. You have another interval worth of source text, and some delta worth of positions inside of them. If we were to just add the total positions together, and then union the sets, which would be what we would do if we were to use these unions, these things directly, we're going to get the wrong answer. We're going to kind of say everything's about the same positions at the start. I've got the first 50 characters, and then I've got the next 30 characters or something like that. And I have a pile of positions inside of that text over here. I have a pile of positions in this text. And if I wanted to kind of glue these things together, what I should do is sort of shift everything that's in this right-hand set over before I glue it together so that the positions are in the right overall place. Does any of that make any sense? I realize now I'm going pretty fast. Okay. So what I'm looking to do is something like this instead of the usual monoid product. But in order for this to make sense, I need to be able to know that A, as a monoid, acts on B, and that this distributes in a nice way so that this whole thing is associative and has a unit and does all the right things. So if we go through and rewrite everything in terms of, I have a distributive monoid action of A on B. I can make some kind of data type that looks like this. So we add up the positions, that's what this is doing. And over here, we're saying take the set of positions on the left and then shift the set of positions on the right over in order to make it make sense. Now these will not necessarily be sets of positions and things like that. We can build CRCs this way. We can build, there's like a kind of common example of like how do you build a hash function that is parallelizable. And one of the naive versions is just work modulo a prime. And so if I take all of the numbers over here and I know how big, like 2 to the n, whatever that is, I can do the same trick in working modulo a prime. We can do that. If you do that in a Galois field, you get CRCs. So you can compute CRCs in parallel. I've written blog posts on this topic. They're available online. I don't need to do the example here. The thread that it exists is a thought, now it's a thought you can think, or you're aware that you can think, and you can find it. So this pops up. There was a paper by Brent Yorgi on what he called twisted functors, which are doing this with an applicative instead of a monoid in the same relationship. So this is sort of a recurring theme kind of in the background. But one of the things that I'm kind of interested in is this. If I were to do a semi-direct product of a group and an inverse semigroup, then I get set of a group and a joined semilattice, I get an inverse semigroup. And so we can see this with this funny thing involving positions. It's not obvious at all that there's a pseudo-inverse or an inverse here. Like I just had, you gave me a set of positions, like an interval of source text or something like that, and you have a bunch of positions in it. Well, what would be a pseudo-inverse for that? Like it's going to be a thing that, it can't get me back to the unit. Like I don't have another set and another delta. I can give you a delta that's going to get me back to 0 delta, right? I can just give you the negation of the window. Now I'm in a negative width. Okay? But there's no set I could give you that's going to cancel out the set or something like that to get me all the way down to empty here. So I don't have a proper inverse. But I could shift the set in such a way that if I were to apply this other thing, it's going to make the set line up magically with all the things I currently have. So it weirded me out that that actually did a thing. So there is an inverse here. I don't know how useful it is, right? If we had some kind of data structure that we were building up that somehow used all this inverse semigroup stuff, I would have an application, like this would give me like another thing that I could put into that kind of container or what have you. I don't have them. So that's sort of my call to action here. Like most of my talks, this is sort of a work in progress where I try and get other people to care about the same kind of problems I care about. So what have we done so far? So we've built a few of these. We played with parentheses, showed that they fell into this framework, that their idempotents were natural numbers with max. We saw this sort of sketched example of taking old source locations to new source locations and vice versa. If I map an old location to a new location and then map it back, I should get, if it survived the embedding into the new locations, I can come back and then back forward and it won't hurt anything. That's sort of the partial bijection bit. And you could see that if you just did the A to maybe B and then the B to maybe A, such that if you survive, if you got a just out of the first step, then damn it, the second one will give, like going back to get the original thing, will succeed, and then coming back will get you to where you came from. They pop out of these semi-direct product things that are popping up all over the place in a compiler that I'm working on, because I've been building a compiler that kind of looks like it was designed by aliens. Who are obsessed with maximizing the amount of recomputation or like shared computation with the previous compiles. So yeah, so please, if you can think of another thing that fits this domain, there's all sorts of stuff that like Girard has involving unification that falls into this inverse semigroup bin, etc. That was where Dan Haraj got interested in this problem in the first place. So I have now passed my obsession with this onto you, and I wish you good luck in finding me new ways in which I can use it. All right, that is all I have right now. Thank you very much.